Great, thanks, Athanasios. I hope you can hear me now.
Yes, we can.
Okay, perfect. Thank you very much. And of course, sorry for not being there. I would want to be there for a couple of reasons. We are in the middle of winter, so it's pretty chilly, and we are in the middle of exam season. So I didn't have a lot of time to put together this presentation, which I apologize for. And when I looked at it this morning, I think I accidentally made an American review talk where I only refer to my own work. So sorry about that as well. Okay, so just to set the scene a little bit on what we're actually doing when we are looking at modeling, we always imagine this kind of simulation chain for solar energetic particles, where you feed the model or the model chain with some kind of remote sensing observation that feeds into an acceleration model. The output of the acceleration model feeds into a transport model, and in the perfect world, the transport model can then be used to make a prediction or explain some kind of observation. Now, even if you're not interested in solar or space weather applications as such, the idea of having a model that can start with remote sensing observations and make solid predictions is actually something we should all aim for. If you look at the basic definition of a successful theory in physics, uh, successful novel prediction is one of the metrics you can use to actually evaluate if your model chain is successful. So in the perfect world, what we want to do is we want to describe all the relevant physics from first principles. So that would be to introduce appropriate coefficients that are derived from theory and remote sensing observations, run the simulation model, and be able to routinely predict SEP event characteristics. And as you know, this has not been done before, and I think one of the questions is if this is actually even possible or plausible. Why is this? Well, because in reality, things are much more complicated. So instead of the simple model chain, in reality, everything is complicated and interrelated. So for instance, for the acceleration model, you need, of course, remote sensing observations of the flare site. This will key, for instance, into a model for the local magnetic field that could be important for the flare acceleration initial part or for the shock forming in the lower corona. You need to know the seed particles and how they get injected into your acceleration mechanism. The acceleration mechanism at the site is also dependent still on the diffusion coefficients. And to know the diffusion coefficients, you of course need a theory for this, but you also need to know the in situ turbulence and how this couples to the particles. If you know all of these, if you have all of these ingredients, in principle, the acceleration model can predict or produce something. This needs to fit into or feed into a transport model. For this, you need probably the global magnetic field from MHD. You need the diffusion coefficients. And in principle, this can then do a prediction. And in reality, this is just too complicated to handle at the moment. So what we usually do, and this is why acceleration is not included in the title, is I think it's not possible to handle both of these at the same time with the same model. So we usually split up the models and focus only on one topic. So I'm going to focus only on the transport part, but luckily Alexis has covered most of the acceleration part better than I could ever hope to do. Okay, so now we look at particle transport, and you essentially have two types of diffusion you need to look at. The one is pitch angle diffusion and perpendicular diffusion. So I decided to maybe split up the two processes and look at them differently. Now, of course, I don't need to preach to this crowd. You're all familiar with turbulence and scattering. But in general, if you need to motivate to someone, why should we include particle scattering at all when you look at SEP events? The answer is simple. The heliospheric magnetic field is turbulent on all scales. So if you look in the left panel, if you look at the magnetic field on scales of months or days or hours, if you zoom in, it's not a smooth Parker field, of course. It's superimposed on top of the background field is turbulence, usually characterized by energy spectrum, for instance, seen on the right-hand side. And as soon as you have a turbulent magnetic field, the particles will react to this turbulence. And how they actually do it is, if you look at the particle level, pretty complicated. So this is a simulation of a single particle just for illustrative purposes, moving in a turbulent magnetic field. So it starts at the bottom, it spirals up along the field. So there's a background field plus some turbulence. If you look from the top, the particle trajectory is still more or less a circular gyration, except that this gyration is a little bit perturbed. So the motion is still smooth, but if you look closely, it's not a perfect circle. There's some small perturbations in there. And if you now calculate for this exact same particle what the pitch angle of that particle does, this is the blue curve as a function of time, you can see the calculated pitch angle with respect to the background field has seemingly random changes where it changes up and down like a Brownian process. So random changes. If you have these small scale turbulence and they lead to these random changes of the pitch angle of the particles, it kind of looks like a diffusive process, and that's what we assume, and then introduce a pitch angle diffusion coefficient that should govern the rate at which the pitch angle changes as the particles propagate along the field. Now, in principle, you can calculate the pitch angle coefficient from some kind of theory. For the theory, of course, you still need to know the solar wind turbulence and the background plasma conditions, or you can calculate the coefficient by comparing a model to observations. And this is one example of recent work that we've done that seems to be give a pretty nice result. So for this work, instead of solving the complicated multidimensional transport equation, you stick to a simplified 1D transport equation where you simulate the solar wind, the SEP particle distribution along a single field line. You only have to care essentially about the focusing term, which for the Parker field we have a relatively firm grasp on, and then we add this pitch angle diffusion term to that. We treat that parameter as a free parameter, and then by comparing the simulation results to the observations, you can constrain the free parameter d mu mu, which you can then use to calculate the corresponding parallel mean free path, which is generally a more useful quantity for comparison. Now, to do a study like that, you need to be very careful for your event selection because you're using a 1D model. You have to make sure your observer is magnetically well connected, relatively well connected to the acceleration site. So to do this, you use this famous solar Mach tool from Jan. You find the position of the event. You assume some kind of Parker field extrapolation. You look at the magnetic connection between the different observers, and then you select just magnetically well-connected observers. In this case, I think it was wind observations at a given energy. You look at the time profile of the measurements, that's the gray circles. You can also look at the anisotropy if it's available. Then you do an optimization process in the model where you vary all the free parameters. You find a set of best fitting free parameters. For instance, on the left, that would be the case of the black line. And for most of these events, we find actually some parameters, some combination of parameters are very good comparison. And as a sanity check, we also compare the anisotropy just to make sure there's nothing weird going on there. Now, in this type of work, we are doing, I would say, to some extent, exactly the opposite that Alexis and his group is doing. we are completely ignoring the acceleration process. So we are treating the source of the particles in completely ad hoc fashion and trying to focus just on the particle transport part. Now you can do this for a bunch of different events for electrons and protons of different energies. And on this plot, all of the colored symbols represent the best fit lambda parallel for a set of observations. So at lower rigidities, so this is all in rigidity, lower rigidities are the electron results, higher rigidities, the proton results, and also added on here with all these letters and symbols, and there's even some Greek letters. That's estimates from previous work. So I think if you look at the distribution of the inferred parallel mean free path, it kind of compares, I would say, pretty well with previous estimates. There's some consistency. And it compares relatively well with this gray block, which is the old Palmer consensus values that we've been using since the late 70s. Now, this is not what we want to do. Well, that's one thing we want to do. We want to have an idea of what the parallel mean free path is from the observations. The second part is to compare the inferred results to theory in order to also test how good the theory works for different events. We've done it in the paper. The paper is now finally accepted. It should be on archive soon, I think, if it's not there already. And there's a figure at the end that summarizes results like this. So the left panel, that's just the inferred results for electrons, the data points, assuming a dynamical turbulence model. So that's the general idea where you have alphenic waves scattering of particles or particles scattering of alphenic waves. The middle panel, it's the same idea, but for a different turbulence theory, which doesn't fit at all. And for the right panel, which is the one you should look at for now, these are the inferred results for protons, all the symbols, and the different lines are different predictions from the old quasi-linear theory that still holds up very well. So what we've done for this work is we haven't just added one line from theory. We've gone through the observations of interplanetary turbulence at 1 AU, and we've also included the variations or fluctuations observed in these turbulent quantities. So for instance, if you look at the correlation length of the turbulence, you have a mean value, which we usually use, but there's also a pretty broad distribution in this quantity. So we've included essentially the deviation from average as well. And if you include these differences for all the different turbulence quantities, you get all these gray curves on this figure. And what's nice, what I like about the figure is if you include these natural variations, which you do observe, it kind of explains why you have this broad scatter in the observed or inferred parallel mean free paths from the SEP events. It's just it happens because of the natural changes in the background solar wind. Also, what's promising from this is the red curve in the middle that says nominal values. That's if you run the simulation just with the average values, and it kind of passes more or less to the middle of the distribution. So everything looks fine. So I think if you look at these type of results, at the moment, I think we have a very good grasp on what the pitch angle diffusion coefficient should be for protons in interplanetary space. I think we have a very good idea. If you look at the left panel for electrons, it's not so simple. So there, all the gray curves, they cover like 3 or 4 or 5 orders of magnitude because of the huge uncertainty in the high frequency range of the turbulence. So it's just so much uncertainty, it's really difficult to actually say if it's a good comparison or not. However, some of these gray curves still go through the data. They show the same shape. And I think that's actually still encouraging, although there might still be issues with the low energy electrons. So that's how far we are with the parallel mean-free path. The question is it important to include this into your model when you interpret electron results? As an example, electron results. The answer, I think, is yes. And this is a case study I always show to motivate why you should include pitch angle scattering. The figure on the left, that is electron spectra from Nina's paper. The black dots and the red dots are for different pitch angles. So for pitch angle of particles moving away from the sun, the red is spectra of particles moving towards the sun. They are different, so that's one thing you need to explain. But this spectra also shows some kind of a bend over or a kink or a break, if you want, where the power law index changes, for instance, from -3 to something closer, -2 at low energies to something like -3 at high energies. So usually if we see something like this in energetic particle spectrum, and we do see these, of course, for protons, you always think it is a diffusive shock acceleration spectrum with some kind of exponential bend over or decay, and this should be explained by the acceleration process. Well, it turns out for electrons, where you have this very weird energy dependence in the diffusion coefficient, you can actually reproduce this by just running the model with a power law injected near the sun, calculating the intensities at Earth. And if you look at the red panel, you see the power law shows this, let's call it a bend over or change in the index, just due to the scattering and because the scattering is so different at lower and higher energies. So this is what I think a nice example showing that how the acceleration characteristics and the transport characteristics could in principle lead to very mixed results. And in order to interpret what's going on, you actually need to make sure that you correctly correct for any transport effects. Whether this will be there for high energy protons as well, I'm not sure. There's still energy dependence. I think nobody's ever looked at it at much detail. Now that's pitch angle diffusion. I think we have a very firm grasp on that. The bigger problem in the modeling is what to do with perpendicular diffusion. At least I have one slide which I use to convince myself that perpendicular diffusion should always be present as long as you have turbulence. It's a basic derivation that by now, hopefully, our plasma physics students are doing in the exam, where you calculate the motion, the drift motion of a guiding center of a particle. And there's a couple of terms. The first term is the guiding center just moves along the field because the particle moves along the field. There's a curvature, or a gradient drift term. There's a curvature drift term. And if you have a Parker field, we all know these curvature and gradient drift terms for the galactic cosmic rays. If you now, instead of assuming a Parker field, assume some kind of turbulent field, so your magnetic field is a Parker field plus some kind of small perturbation, and you do the calculation, you actually see that your drift terms actually split. So there's a deterministic drift term, so that's the normal galactic cosmic ray drifts. Plus there's a random drift component, and there's an example of that at the bottom that depends just on the turbulence quantities. And the idea is how to interpret this. As soon as your magnetic field becomes turbulent, of course, it has squiggles and wiggles on top of that. That will lead to local gradients in the field and small local curvatures of the field. And these gradients and curvatures can then force the guiding center to move from one field line, one turbulent field line, to a next turbulent field line. The first term on here, speed times pitch angle, that's still just the term describing particles moving along fields, except now it says particles move along turbulent magnetic fields. And that term gives rise to the well-known field line random walk idea, where the magnetic field makes random excursions and the particles just follow these random excursions perpendicular to what the Parker field would have done. So at least mathematically, once you have turbulence, you have perpendicular diffusion as well. The question is, how big is this effect for solar energetic particles? So is there evidence for perpendicular diffusion? I would argue yes, some would argue no. Is there a smoking gun somewhere? So is there a specific observation or set of observations that can only be explained by perpendicular diffusion and, for instance, not by extended source? That I don't know. I'm not aware of something like that. For every person that wants a perpendicular diffusion dominated scenario, you will have Coulomb-Vaques that can explain it with back mapping to some kind of shock. So it's really a difficult thing to disentangle. But there's possible evidence, and I think part of these coming years we will re-examine a couple of this. So the one thing that's interesting, and this is still, I think, from Nina's PhD for the stereos, the left panel shows for these, I think, is for widespread electron events, the maximum anisotropy observed as a function of magnetic connection. And there's an interesting distribution. So generally, if you're magnetically well connected to the source, you find a higher anisotropy. If you're magnetically not so well connected, you still find particles, but these particles tend to have a much lower anisotropy. So while perpendicular diffusion included in the model can explain this quite naturally just due to the scattering or additional scattering you have to move perpendicular to the mean field or away from base magnetic connection. So anisotropies might be one way in which to distinguish source size versus perpendicular diffusion. Second one, and I'm very, very happy Ian is online for this, is in his paper, Richardson et al. 2014. If you look at the onset times of SEP, MEV electrons and protons, and you try to explain the angular dependence of the onset, if you neglect all particle transport, you make some simplifying assumptions, you would probably need electron and proton sources that expand at different rates for electrons and protons. I mean, this is not impossible. You could have expanding shock. The source regions for the electrons and protons could be different. But I would argue, on the other hand, if you have a field line random walk process where the diffusion perpendicular to the field scales with particle velocity, it's a nice natural explanation of why these different distributions seem to broaden at very different rates. And we can explain this linear onset time dependence, I think, pretty naturally. Another of examples, and this is things that we haven't looked at yet, but it's on the to-do list to do, is a paper by the late Stephen Kaler, where his group, they fitted the Gaussian distributions as a function of time to multispatial of events. And one of the quantities you get from the Gaussian is the broadness or standard deviation of the Gaussian. And if you look at some of their results, so for instance, this would be the open symbols, it appears that the broadness or standard deviation of the Gaussians increases linearly with time. Of course, again, you can explain this by an expanding source probably, but this is also a natural explanation or the natural result that you get from a diffusion process where a Gaussian increases linearly with time proportional to the diffusion coefficient. So this would be something also to look at, especially for more events. I think they only have 3 events in this paper. Then something new, which I know the graph is still a mess, might be interesting to look at. There's a new paper from Arik in press now, where, and I paraphrase his results heavily, where it appears that if you do a velocity dispersion analysis, the apparent SEP path increases with decreasing magnetic connectivity. So you find very reasonable short SEP path lengths if you're magnetically well connected, but if the magnetic connection gets worse, it looks like the SEP path lengths tend to increase. So somehow I've tried to plot this on the left figure, where as soon as you move away from magnetic connection, there might be an increase in the path length. Some of the data on here, I think, comes from the Pasita et al. Paper. It's very preliminary result. Don't take it too seriously at the moment. But this would also be something that could, in principle, be explained by perpendicular diffusion. That's probably more difficult to explain with a expanding shock, because as the shock expands, presumably gets closer to the observer, so the VDA length should decrease, although, of course, there's always, for each event, the case to be made that there are more complexities involved. If you look at energetic particles, you also have to look not just at the solely energetic particles, but also at the other particle populations. This is a case of simulations of Jovian electrons. And we all accept for Jovian electrons, there's significant levels of perpendicular diffusion that you need to include. Electrons are electrons, so if Jovian electrons suffer perpendicular diffusion, SEP electrons should do as well. And of course, I have to add this in here as well. If you look at galactic cosmic rays, the only reason we observe galactic cosmic rays at Earth is due to perpendicular diffusion of GCRs perpendicular to the Parker magnetic field. If perpendicular diffusion wouldn't exist, we wouldn't have any GCR. So there are some convincing cases that you need to also have perpendicular diffusion as well. Now I've added just one slide in here. So I've talked about the pitch angle diffusion, the perpendicular diffusion. It has to be included into models, and there are a couple of models that do include this already. The question is, what's the current state-of-the-art model? And the one example I always like to show is the model from Nicolas Veysen, the Paradise model. I think at the moment, this is the state of the art when it comes to simulating particle transport. It's a magnetic MHD generated background magnetic field. On top of this, you have the SEPs introduced as test particles. They suffer both pitch angle diffusion and perpendicular diffusion. And that's the best we can do at the moment, I think. However, this is still very, very, very far from this complicated model chain I introduced at the beginning. Even for these, I think, very, very state-of-the-art models, the coefficients are still chosen ad hoc. In an ad hoc fashion, it needs to be optimized in order to fit the historical SEP events. There are huge questions about the seed particles, how they should be accelerated, whether or not the MHD shock goes low enough into the corona to actually initiate, for instance, GLE type particles, and predictive simulations are not yet possible. So even with these very complicated, computationally very expensive models, it's still not a full story. And the question is, why? Why do we have this very limited progress? And I could think of two examples which I list here. The one problem, each SEP event is different. I can't keep track of the events with the different dates and numbers, but each event these days has its own paper, and in there are very detailed complexities relevant for each event. So what we do in models, in order to simplify everything, in the model you assume the magnetic field is made up of three components. You have your Parker magnetic field, which is the background magnetic field. On top of that might be, let's call it mesoscale structure. So this would be like maybe CIRs, fast, slow wind, or variations in the solar wind that gives some deviations from the Parker field, but still deterministic structures. And on top of that, you will have large-scale fluctuations, or what we would normally call turbulence. Now, what we do in the model, you can easily do an average, which is equivalent to setting time to infinity. So you're essentially sitting at the observational point, you measure the magnetic field, you average infinitely long, you average over all of these mesoscale structures, you average over all of these turbulent structures, and you just have a Parker field. And then you simulate your SEPs in this Parker field structure. And of course, that's not the case in reality. In reality, the solar wind has structure. And if you include some of these mesoscale structures or solar wind variations or whatever you want to call it, it leads to very different results. So the figure on the left, this is the perfect model particles propagating in a Parker field. The figure on the right is where some of these solar wind fluctuations are captured that influence the magnetic field at intermediate scales. And if you solve the particle transport on top of that, you get this jagged distribution of solar energetic particles. So some magnetic field lines have more particles than other ones. And now an observer, in observing the event on the right, the observation or the time profile that it will record depends heavily on the position. If the observer was 2 degrees to the left or to the right, it would actually measure a completely different time profile, and it would even look like a different event. So this is one issue we have, how to capture these deterministic deviations from a Parker field. The second one that's just as difficult to solve is, except for these mesoscale changes in the magnetic field, you also have very large inter-event variations. So of course, the size of the SEP source will differ. If it's a shock, the shocks have different width, they expand at different rates, they move at different rates. Each CME shock is slightly different. Each flare is slightly different. There might be different seed particle populations. They might have different distributions, so their density could be different, their temperature could be different. There could be different cosmic ray transport conditions in the solar wind, as we've seen already, and all of these small differences might add up and lead to very large differences in the resulting SEP event. So we've had an idea and looked at this before to actually see how large such effects would be. We do some type of ensemble modeling where we run the SEP model with slightly different parameters. So some variation, for instance, in the solar wind speed or parallel mean free path. The problem is that the transport equation is nonlinear, and these small differences add up and could actually lead to very large variations in the resulting time profiles. And these are some examples of what you might find. So the left panel is for magnetically well-connected observer. If you just fiddle with these, I would say, relatively small changes to the different parameters, you have these very large difference in time profiles. If you're magnetically disconnected, it gets worse and worse to the right. And if you're on the opposite side of the sun, you get this right panel, and it's simply just a complete mess. It might be exaggerated in these simulations, but I think we have to keep in mind that if you do a model, you're kind of simulating the average or the mean SEP event. And this mean SEP event, whatever that average is, simply doesn't exist. So this makes life very, very difficult from a modeling point of view. So if I have to summarize the talk, I think we have a firm grasp on the pitch angle diffusion coefficient near 1 AU, and it seems to be valid if you move inner towards the sun as well. So I think we have a pretty good idea what the pitch angle diffusion coefficient should be. Perpendicular diffusion is an ongoing problem. There are some theoretical issues. We don't have a lot of, let's just call it mature, consistent theories on what the pitch angle dependence, for instance, of this coefficient should be. And it's very difficult to find a suitable model data comparison that gives unique results. We can really hammer down, this is how large the perpendicular coefficient should be in general, or what's the role of the diffusion coefficient versus the source region size, for instance. Next point, I think most of the physics we are looking at should be applicable to higher energy SEPs. At least for the diffusion coefficient, it looks that way. Of course, it might be that some physics is still missing, and this is also in Alexis' talk. We might have wave amplification, especially in the acceleration region, but also for escaping particles. Drift effects might become more appreciable at higher energies. There's some issues with the current sheet that's still not solved, if it's really a diffusion or a propagation barrier for particles or not. So there's some, hopefully, I would say, second order physics problems that should still be included. Then for the model data comparison, there is a lot of inter-event variations due to magnetic structures, initial conditions, seed particles, etc. I'm actually starting to doubt whether it actually makes sense to simulate an individual SEP event with a model at all. Do we really learn anything from comparing a single SEP event to a model where we have to fine-tune the parameters to actually fit the event? Or should we rather only look at the average behavior and compare that to a data ensemble, for instance? And if yes, what kind of ensemble? How will you separate the different events into gradual, impulsive, electron-rich, proton-rich? What's the average? So there's I think a paradigm issue with how to actually compare the model to SEP events. And on top of that, what characteristics we should compare with to examine the different physical parameters. And with that depressing thought, I think I have said enough. Thank you very much, Thanasis.
Thank you. Okay, any questions in the room? Alexis.
Hi, thank you very much for the talk. Can you hear me?
Yes, sir.
Yeah. So what about dropouts for the perpendicular diffusion coefficient? Are these still not, there used to be an argument against large perpendicular diffusion, at least under several MeV.
Yeah, so I think it comes back to this idea of I think averaging, right? So if you look at the figure on the left, where you have large scale field and you have what we call normal diffusion, you have this nice smooth SEP distribution, you can't have dropouts, right? It's inconsistent with diffusion. But in reality, we never have this picture on the left. What we probably have is something more towards the right, where the entire heliosphere is not filled with magnetic field lines that originated at the active region. Some field lines connect to observers, some don't. So in principle, you have something that looks more like the right-hand side, where you have filled and empty flux tubes, which again just illustrates the fact that we are not, in these diffusion models, we are not capturing these unique features in each event. What we would say is, if you look at SEP events and you average over an infinite number of them, you should get the left-hand picture without any SEP dropouts. In reality, you get something on the right where there can be dropouts because this specific ensemble didn't have a filled flux tube at the position of spacecraft X. So I think in principle, yes, it's inconsistent with diffusion in the average picture, but it could still be explained by just realizing that when we deal with SEP events, we can't just let time go to infinity. You have a finite event, and some of the features in principle can't be captured with the diffusion process. That makes sense.
Okay, yeah, thank you. Another question, I'm not sure if it's a question, but more of a remark. You know, with PSP, we see all these switchbacks all over the place.
Yep.
And they large scale turnings, so I don't think they will lead to diffusion as such, but they're going to change the behavior of the particles.
Yes.
And they may be reflected, the path may be much longer than we think, and so on. And I'm wondering if there's a way of addressing that.
Yeah, that's a really difficult question, and that's That's one of the problems with this whole idea of using these models for prediction. So when the particles get released from some acceleration site closer to the sun, there's no way for us to sense or measure the in situ magnetic field that the particles experience from the corona out to 1 AU. So one particle might be lucky, it doesn't see any switchbacks, it just moves along something that looks like the Parker field and fits perfectly to the model. The second particle might interact 7 of these switchback structures. We observe something with a lower level of anisotropy and a very strange pitch angle dependence, and we have no way of determining the history of this particle for that specific case. So that's part of the question of these mesoscale structures. So is it actually even possible to add these? Yes, the large scale magnetic fields we can add, but I mean, as you know, if you look at the comparison, there's always these. It's not turbulent fluctuations, but these small-ish scale fluctuations in the field that can never be captured by the MHD. So I'm always wondering what the effect of these mesoscale structures would be on the particles, and probably switchbacks are like one good example of these structures.
Yeah, it's hi Du-Toit, this is Bernd speaking. So
Hi,
very nice
Bernd.
talk. Coming exactly back to this point, I'm here, which you show the delta B should be 0. But in principle, if you take Timo's idea of wandering field lines, there's no reason why this should be, I mean, in infinity, yes, but the particle, the time is not becoming infinity. So even that already would tell you that delta B cannot be 0.
Yeah, of course, delta B can't be 0. That's and somehow this is governed by the time scale of the particles, right? So if you have an electron event at the sun, the electrons would take, let's say, near relativistic electrons 10 to 20 minutes to reach Earth. They only average, or they only experience like a couple of different turbulent structures, and this whole formality of time going to infinity is not possible. So I think the way that Timo does the wandering field lines, that's one step better, right? So instead of assuming a Parker field and some magic diffusion process on top of that, you can directly follow the particles along the wandering field lines. But that's still not the full picture, because if Timo runs his model for an infinite number of particles or for many particles, he still gets this smooth-ish structure on the left. It might be broader or not broader, but for instance, it still doesn't have the dropout. So we're still missing some details inside of this, what the field does. And I should mention in this sense that the Thailand group, and I cannot remember the actual reference, but one of the Ruffalo et al. Papers, I think it was not led by him, by a student. They have some simulations where they don't look at the diffusion limit at all, but they simply have an active region and they have some real magnetic field lines coming out of that, and they follow just full orbit simulations, real particles. And probably that's closer to reality, but what happens in reality, but you can never simulate something like this for a specific event, because you don't know the exact trajectory of the particles between you and the sun. So we're still kind of caught in this. We can do it more complex, but it might not be applicable to a certain specific event, and this is still a big problem.
Yeah, I definitely agree. I mean, what you're not showing here is the connectivity within the corona towards the those are called injection areas. So what is the injection function whenever this goes out in the interplanetary medium? But another issue, it seems to me, everybody forgot about the Fisk field. So you showed very nicely this plot for the high latitude. And I think this is definitely not what will be there. So if you
No. Yeah. No, definitely.
So how would you try to incorporate that?
I mean, the first field itself, I mean, that we know how to handle it, like the large scale field, right? But I think you'll still be left, yeah, with the same problems with these mesoscale structures. But that at the time being, we are just stuck in the ecliptic, and even in the ecliptic, we cannot solve the problem. So I'm actually scared what will happen if solar orbiter moves away from the ecliptic. I mean, we are just complicating a problem that's already at the moment intractable. So sure, we should include the first field, but we still have some other questions as well, which we don't understand how to handle.
So if I'm allowed, that's another question. So on one point, you showed some latitude dependence. And there was a restricted area where it goes down. Is that also correlated with the tilt angle?
This might be not latitude, but longitude, right?
Ah.
So
Okay.
I think it should all be azimuthal angles. So just ecliptic results at the moment.
Okay, sorry, we took longer than expected, but it was interesting. Kouloumvakos, you want to say something?
Yeah, just something very quickly. So I would like to focus on two very interesting questions actually that you posed in your presentation. So the first was if there is a smoking gun, let's say event or events, and how to find these cases. And the second very interesting question was why we haven't really progressed so much in the case of the perpendicular diffusion. So these are really interesting questions, and we have to think about them. So for the second question, how we haven't progressed that much, my feeling is that you know, we have stick a little bit on the old philosophy, let's say, that you know, assumes point sources, and usually when you have a wide source, you exclude the wide source and you start playing the game without it, trying to understand perpendicular diffusion, and that's a, let's say, a problem, okay, because so there are events that, so one story, for example, in the event of the 20 November of 2020, I think it was, in that case, we saw that, for example, we had a wide source. It could explain some of the observers. For Earth, it was a little bit questionable, but we saw a pressure pulse hitting the streamers that might be connected to Earth. For the GLE, we find some similar stuff. So we said, okay, for many of the observers, again, the shock might be responsible, etc., etc. And then we have the September event. It's the famous event on 2022 that PSP observed, and we have an analysis of this event, and we found that you know, even the connectivity was 60 degrees apart. If we assumed perpendicular diffusion, then the results would not be consistent with the observation. So there's a mixture of things, and when you have, you know, a wide source, you never know. So that's an issue. So now I'm going to focus on the second question. How to let's say, recognize a smoking gun event that might
Sorry,
show
Thanasis. Sorry, Thanasis, if you hear me.
I will be very, very quick. I'm just finishing this up. And I think, you know, we have to
There is
find
an
something.
anti-correlation between quickness and all this. Okay,
Of course.
We need to cut you down.
Yeah,
because
but
we are already.
it's only a sentence. I mean.
Okay, so thank you for your comment, and thank you, Du-Toit. Really appreciate it. So, Eleni, no, you should move forward. Thank you, Du-Toit.
Thank you, Thanasis.